Thank you for being in the room. Thank you for being on time. It's very important we keep time because I know some people are already having to exit and take flights, etc. So thank you. And thank you for those who are still with us online. I appreciate that as well. So we're going to continue the infrastructure and supporting technology. And I'm going to invite to the stage Tim Eismann, who is from Zentrum Hannover. And he is going to talk about the test stand for simulating and analyzing lunar thermal conditions in laser beam melting of regolith. Please welcome him.
Yeah. Hi everyone, thanks for being here at that late hour basically. And yeah, the test stand Lisa already mentioned is part of the Moonrise project, which is a collaborative project between the Zentrum Hannover and the Technical University of Berlin. And our vision in the project can be seen here in this little video. We want to build a space-qualified laser mounted on a lunar rover and use it to melt regolith on the lunar surface in order to produce infrastructure elements or just do general dedusting. And we call that process mobile selective laser melting. Our next goal is to prove the feasibility of the process on the lunar surface, and therefore we signed a payload service agreement with Astrobotic. But before we can go to the moon, we need to develop and validate the laser and the process behind it. And that is pretty challenging because in order to develop a process here in a terrestrial laboratory and expect it to work on the moon as well, you need to simulate the lunar environmental conditions, such as the regolith, for example. You can use simulants, the vacuum, you have vacuum chambers, and also the gravity. For that, we have another project with the same collaboration where we use the Einstein elevator Marvin presented earlier today to determine the influence of the gravity on our laser melting process. However, today's talk is about the thermal conditions, because the thermal conditions are important for laser processes and we need a setup that can monitor these. So first of all, here's our laser. So inside that housing that is pretty small, we have everything we need. We have the laser beam source, we have the electronics, and we have the optics. It weighs less than 2 kilograms, and it will be mounted on the outside of an Astrobotic lander inside a thermally controlled enclosure, and Astrobotic will also provide us with a galvo scanner. However, in our laboratory, it looks a little bit different. Until now, we had the setup that you can see here. We used an engineering model of our laser, and we had a small vacuum chamber. And with that, there are some disadvantages. At first, if you look on the top left, you can see a typical sample of us, and from the outside, you can't really tell much about it. If you wanted to have a deeper insight, you need to do cross-sections, CT images, or do additional tests, and these tests take time. So it would be much more efficient if we could gather some information about thermal properties like cooling curves, heat distribution, and melt pool temperature. And if we did that, we also would have a much more comprehensive process development. Another issue we had with the setup was what you can see here in the blue curve of this graph up there, because that's the pressure in the vacuum chamber, which rises after the process started and it stays elevated, even though the pump is still running. And we also realized that the chamber heats up to some on an unintended way, and in order to have a good repeatability with the process, we need to measure that and determine that. And lastly, the lunar surface temperature is different than it is on Earth, depending on which literature you use. And we also need to simulate that to some extent to have applicability for our process on the moon. And that's why we adapted our test setup to what you can see here. we have a bigger vacuum chamber with our powder bed still inside. Above that, we have a processing head that has the same beam as the flight model, but we also have a beam expander to change the spot size of our laser beam, and we have a pyrometer with a coaxial camera to see inside the melt pool. We also equipped the setup with an infrared camera and thermocouples, and we also have some additional or optional heating elements to heat up the powder bed. And we used that setup to do some preliminary tests, just to show you what is possible with that. Our first experiment was to figure out the influence of the hedge distance, which is the distance between the scanning lines there, the 2 millimeters, for example. And we used the parameters written in the table here. And also we had a thermocouple, two thermocouples inside the powder bed container protruding into the powder bed. And the results can be seen here. Here you can see our samples. They do not show significant differences in terms of dimensions or mass. And we saw that with a smaller hedge distance, we tested 2, 3, and 4 millimeters, by the way. With a small hedge distance, the surface gets smoother. That was expected, but what wasn't expected is what the thermocouples have been measuring, because the red thermocouple here on the left, on the outside, is actually further away from the heat source, from the sample in that case, than the blue one on the bottom. So you would expect that the blue one heats up more than the red one, but it's the other way around, indicating that there is some additional heat source from the outside heating up the powder bed, like radiation that gets reflected, for example. And for us, it's important that we know that and that we can measure that, because otherwise we would have some influence that we couldn't take into account. And then we also had the infrared camera looking inside the processing zone. And in a moment, you will see in the videos the temperature on the top right. That's the maximum temperature for a time. And this temperature might deviate of approximately 5% from the real temperature, but it's still comparable in between these videos. And you can see for the first melt track, the temperature is a little bit lower as for the additional melt tracks. And you can see that some of the the melt tracks are getting remolten again. And you see that the process gets much more stable the more lines we are melting. If you take the data out of this video and put into the heat map that you see on the bottom, there the color coding is for the number of frames or the time that a certain pixel in the video has seen a temperature of above 1250 degrees Celsius, which is approximately the melting temperature. And with that, we see that there is some heat accumulation on the top part of the sample, so basically where the melting starts. And we can see in the right picture of the 4 millimeter that there are some areas in between the melt tracks that have never seen this temperature. And if we looked inside our samples, we would see that there's a higher porosity in the samples and that there are also some unmolten particles inside. But with that solution, with the infrared camera, we can see that right after the process, so we don't have to look inside the samples anymore, and that's why our process development will be much faster with that option here now. And yeah, then we did another test with the setup. Therefore, we used the heating elements to preheat the powder bed from the bottom to the top in order to test if an elevated powder bed temperature, like it might happen on the moon, influences the process. There you can see our process parameters, and it's important to say that we had a movable thermocouple that is going on the top of the powder bed surface in order to measure the temperature there. In that case, we did like only single track samples. And the results show us the following. We can see that there are on the elevated temperatures of 60 and 70 degrees Celsius, that these shapes are more homogeneous on the surface. There's not much of a difference in between these elevated temperatures, but there's a difference compared to the samples with ambient temperature. And if we look into the data, we see that with elevated temperature, that the mass of our samples is higher and that the dimensions are lower, indicating that there is a higher density inside these samples. But there is a little issue with that setup because the way we heat the powder bed is a little bit inverted to how we would find it on the lunar surface, because on lunar surface it would be hot on the top and colder on the bottom. We have it the other way around, so we need to improve that. Yeah, and that already brings me to my conclusion. We have shown that our new experimental setup enables real-time thermal process monitoring, and our way of doing the process development is much more precise and efficient now. We have seen that the hatch distance doesn't really impact the mass or the dimensions of the sample, but it had an impact on the surface, and we have seen that the 4 mm hatch distance is too high in order to have a fully molten sample. And we could also detect and measure the influence that I've mentioned before with the preheating of the powder bed. We still need to improve our setup regarding the preheating with some contactless heating and measuring, and we will further investigate that influence. And with that, I want to thank the German Research Foundation for funding the project with the Einstein elevator, and I want to thank the Space Agency of the German Aerospace Center for funding the Moonrise project, and of course I want to thank you for your attention.
Thank you very much to Tim. So, do you have any questions for Tim? We have a question at the back.
Timon Schild from ESRIC. Thanks a lot for your presentation. I was wondering if you had experienced any plasma formation, kind of at the pressures you're working on with the laser, and also if this is something you would expect in the lunar conditions, and how you think it may affect your process.
Thank you for the question. Actually, we haven't measured or seen that. Doesn't mean that it might not be there, and I'm not entirely sure if we expect that to happen on the lunar surface. Probably, but I haven't got really deep into that, so can't really answer that.
Thank you, Timon. Another question from the floor? No. Thank you very much, Tim. Thank you very much for your talk. Thank you. Next up, we have Johannes Becker from Lunex Technologies, who is going to talk about recent advantages on lunar regolith simulants for European research and its characteristics. Welcome.
Hello, everybody. I'm Johannes Becker from Lunex. I'm pleased to be here. I would like to introduce you to our lunar regular simulant system. The motivation to it is pretty much that we had in the past quite a lot of research projects within a lot of different simulants were developed to pretty much represent the lunar situation. But the problem was there were very specific applications, very specific developments of the simulants. Often only small quantities were developed, so if you ask around, you often get still a few kilos which are left over, but if you continue your work and you request another kilo next year, you often don't get any more. Limited availability that fits to it. Then often inconsistent in quality as they were produced in small batches. Then next point is the characterization. Often this was only done for pretty much the very application it was designed for, and then to it often a high cost, as a lot of research projects pretty much factored in a researcher for a long time pretty much designing, developing this simulant system, not very cost effective. So Lunex Technologies, as a spin-off from the TU Berlin, we were one of those universities who developed their simulants for their use, but also provided smaller amounts to others. And then we noticed that the requests were just too many for us to handle as a university. So we made a small side business out of it, with the aim to pretty much make the lunar simulant systems available to you on a commercial basis, and to bring by that a benefit to the community. But now the question is, how can we actually meet all your applications? As we had our very specific own set, but you have obviously far different one. Let me start with the lunar regolith by itself. It's a very varying mixture of portions of different minerals. often thermal affected materials like agglutinates, glass in it, but that's often not really relevant. Sometimes rich in certain minerals like ilmenite, olivine. Then you have obviously different applications for it. Think of chemical reactions. As Tim presented just before me, he's shooting with a laser on it, so optical properties are very relevant, and that is why we decided to go for a modular system to cover all your needs and to adapt to that. You can see on the left the two, we call them base simulants, LXM100, M for Mara, so lowland, and then we have LXT, T for Terra, and the 100 means pretty much 100%, so it's pure material. We can adapt this to local mixtures by pretty much making a 50-50 out of it, then we call it LXI, intermediate. But we could also think for example, for the South Pole, where we have about 90% unauthorized. Then we go for LXT 90 and 10%. The rest is pretty much the Mara. And if we need further adaptations, then we can think of sintered elements at these to the mixture you get provided. On the other side, we can pretty much generate glass particles, add those to it. We are pretty much thinking of 0 to 40% depending on your application and your needs. And by this, we get to the advanced simulants. And when we add further special minerals like olivine, ilmenite, iron, depending on what you are looking for and you want to work with, we can get by this to the chemical adapted simulants to pretty much cover all your needs, but still be cost effective. We started the whole work by looking out for feedstock raw material we can actually work with. Christopher in the last session introduced you to the Volcano institution. We collaborated closely with them to be in line with either plans and thoughts. In general, we looked for material that is as close as possible to what we find on the moon based on Apollo analyzers. So chemistry and mineralogy is there the key aspect. Then we wanted to have as little alterated bedrock as possible, so no trees, no plants in there, a very low water content, and we wanted to have a long-term availability. So by that we are pretty much the worst customers for the mine to get the feedstock, because we just buy a low ton number, but we always want to have the best material freshly excavated. And yeah, we did this, got to our base materials, the Mara and Terra. And here I'm very thankful for the characterization done by Joel Patzwald and some other colleagues of him. He just recently published a very gigantic characterization of our material, properties of novel lunar helix regulus system. I will often cite in this presentation. I will go over these numbers very quickly, not to get you asleep. This just gives you a brief introduction to pretty much the mineral composition of LXM. You can go through the list. It's an olivine-rich basalt. And you can see on the right the particle size distribution in comparison to what we have in the Apollo samples. And the line in the middle, that is where we are. We focus on particle sizes from 0 to 2 millimeters. That is where we are a bit different to some other competitors. But upon your demand, we also can provide just particle size fractions, so 0 to 100 microns, depends on your needs. Then we get to the physical properties, also just a very brief overlook. We have solid density, bulk density, all these data are available for you. As I already said, the characterization is very holistic, 23 pages long. You will find a lot more there. And then in comparison, the chemical composition to some other places, some Apollo probes, and you can see we are often very close to pretty much what you find on the moon, and often within the tolerances we also get from pretty much the samples there. With this, LXT is a ferro-anthracite with a composition shown as over here, and also the particle size distribution and the physical properties. If you have any questions, please approach me afterwards. We have also some samples outside you can have a look at, and I'm happy to provide data sheets. Yes, and with this I would like to get to actually the summary and outlook. I made you familiar with LXM and LXT100. Fully characterized, we're very pleased about that, so thanks again therefore. But we have on top of that also Mare glass and Terra glass prepared, several kilos already well prepared. We are currently working on agglutinates to add these. We already have some, but we want to further improve them. Then we have the additives and the whole part, the adaptability, sorry, that is pretty much what Joel and his colleagues are going to publicate soon in a second paper. And on top of that, we have freshly or new in the program an Alex Mars, a Mars simulant. It's a global fly sand. In case you're interested about that, you are welcome to approach me. And with that, I'm already done. Thank you.
Wonderful brevity here. Fabulous. Any questions? Front row.
Thank you. You might get bored today with my questions. I have a question about iron this time, however, and namely the difference between Apollo samples and your samples. I notice your iron content is twice smaller than the Apollo samples that you cited. What is the reason for that?
That's pretty much due to the stock material we use. But to my knowledge, that's pretty much often what you have on Earth. But you also need to consider the aspect that we are looking on the moon for iron in a reduced oxidation situation, so FeO, not Fe2O3 as we have it here. So there's always a certain difference always given.
10%.
Yeah. Okay.
Thank you.
Okay.
Thank you.
Anyway, very nice talk.
Thank you very much. Any other questions from the floor? No more questions. Thank you very much. Thank you, Johannes. Thank you. Next, we have Lennart Fox from the Fraunhofer Institute for Production Systems and Design Technology. And this is from TU Berlin also. And he's going to talk about graphite components for lunar in situ resource utilization.
Thank you for the introduction. As said, I would like to talk about graphite components that we've recently manufactured for some people on this conference at the Fraunhofer Institute for Production Systems and Design Technology, located in Berlin, Germany. I would like to first introduce you to graphite and why it might be interesting for ISRU applications. Then I will highlight on the challenges and how we overcome them when machining this material. And lastly, I will give the examples and show you what they were used for, or are being used for actually. So let's start with graphite. When I say graphite, what I actually mean is synthetically produced graphite, not the material you find in mines all over the earth, but artificially produced graphite, which is basically a matrix of carbon particles in the size of 8 to 15 microns, and they are basically polycrystalline material, which is being used in a various range of applications due to its properties such as the high temperature resistance and low thermal expansion under these high temperatures, but also the very good thermal conductivity, high specific heat capacity, excellent chemical stability, and low electric resistivity. And all these properties render graphite a useful material for electrodes, crucibles, molds, nozzles, but also in many other applications. I'm sure you can think of some applications by your own. On the right-hand side, you can see two examples of die-sinking electrodes that we've produced in the past to sink them into metal to produce a mold for for plastic injection molding in these cases. So now that you're familiar with the material, let's move on to actually machining the material. And for that, I would like to introduce you to the Institute for Production Systems and Design Technology, short IPK, in Berlin. What you see here is a picture of the institute, and the round building in the middle is our shop floor, which is more than 10,000 square meters large, and where we host a wide array of different machining capabilities. If we have a look from the top, you can see the round building. This is our main shop floor, and then on the bottom we have our application center for micro production technology. This is where we also have our high precision laboratory and our ultra precision laboratory. These are temperature controlled to ±5 degrees centigrade, and therefore allow us to go even into regimes of higher precision, combined with our excellent machining capabilities. This is also where we house our 2 clean rooms, which we mostly use for biotechnology applications and coating experiments. So let's have a look at the manufacturing capabilities. This is obviously just an excerpt. It goes way beyond this, but our manufacturing capabilities include the high precision machining. Here you can see an example where we machined a nozzle for a custom 3D printer for a customer. Below that you can see an example of one of our laser microstructuring services, where we microstructured a surface to be less susceptible to biofilm creation on implants. Next to that you have a trial of 3D printing electrodes for die sinking. And the die sinking is also where our graphite machining capabilities come from, because, as I said before, graphite is being used for electrodes for die sinking. Obviously, we need metrology capabilities. This is especially then the case when we talk about ultra precision machining, which you see in the top right. Ultra precision machining is machining of components where the surface plays a very crucial role, mostly in the range of nanometer accuracy. So, for example, for optics, freeform optics, lenses, and so on. And below that, you can see a SEM image of our wire EDM experiments that we did in the past to determine basically the minimal possible manufacturing for wire EDM. So let's move on. So let's move on to actually machining graphite. As I said before, graphite is a compacted carbon matrix, basically. So when you start cutting it, graphite is quite brittle and also quite soft, actually, but the individual particles that you create while machining it are very abrasive. And the material itself is quite porous, actually, so it acts like a sponge, and you can't actually use cutting fluid like you would on, for example, metals, because on the one hand, the material would absorb the cutting fluid, and on the other hand, the abrasive particles and the cutting fluid together would create a very abrasive slurry that then destroy your tools and your machine. So yeah, you can't use cutting fluid, and you have to avoid some cutting properties because of the brittle material properties. So what are the approaches that we've utilized to overcome these challenges? First of all, we have a particle removal system that gets rid of, with vacuum basically, it gets rid of all the dust or the particles that are being created during the machining process. This is good for keeping the machine clean basically, but also for our health, because the carbon, you don't want to breathe these carbon particles. Further, we use diamond-coated tools, and we use a very low theoretical chip thickness. I'm saying theoretical chip thickness because these are not actually chips. We are not actually cutting the material. Instead, we are more breaking the material. So, now that we've established why and how we would cut these materials, I would like to introduce you to 3 examples of actual components that we've manufactured and designed in the past for companies on this conference, such as Orbit Recycling. I'm sure many of you have seen the technology demonstration outside, and their rovers, or they have a concept where their rovers would pour molten metal directly into artificially created trenches on the lunar surface to create cables or structures on the moon. And for that, we have designed and manufactured a nozzle, which you can see on the right-hand side during the manufacturing process, out of graphite. Graphite here was used mostly because of its temperature resistance, basically. Next up, I'm sure many of you are familiar with Simon's work at TU Berlin. He has a vacuum chamber with a crucible surrounded by an electric heater to melt regolith and then extrude it through a nozzle and into usually a powder bed. But the idea was to replace this powder bed with a mold to do casting of glass samples, basically. And we have created a little graphite mold for that. Because we are working in vacuum here, we don't have to care about the temperature, actually, because graphite in vacuum goes up to 3000 degrees centigrade in thermal stability. And on the right-hand side, you can see the experimental setup. On the top, the vacuum chamber, and in the bottom, the graphite mold with the freshly molten regolith. Let's zoom into that. Just after the extrusion, you can see the material as it solidifies, but then, surprising, the glass didn't survive the thermal tensions and basically exploded into the vacuum chamber. So the lesson learned is that we have to do some sort of annealing in the future to also heat up the mold itself. And this is exactly what we are planning to do with the advanced mold for regolith casting for a use case by Polymark. I'm sure also many of you have seen by now the transportation and processing system from Polymark outside. Basically a helical tube that rotates to transport the regolith wherever you need it to be. And the idea is to create a 3-part mold for a segment of this tube. You can also see one half of the mold outside. We just very recently started this project, so it's still an ongoing endeavor. But the basic idea is to have this 3-part mold. The blue part would be the casted part in the end, and we add 2 heaters and temperature sensors to monitor the temperature and to being allowed to basically anneal the part while it is being cooled down. And that concludes my presentation. Thank you very much for your attention, and I'm happy to answer your questions now.
Thank you, Lennart. Thank you very much. Thank you. So do we have any questions for Lennart? I don't see any hands. It's got very, very quiet. You used up all your energy in the first 2 days. No questions.
All right. If not, you know where to find me. I'm outside, and see you then.
Perfect. Thank you so much. Thank you. Thank you. Next, we have David Pearmain, who is from Lucideon Limited and is going to talk about flash sintering of lunar regolith simulant.
Okay, thank you very much. Yeah, my name's David. I'm here to talk to you about flash sintering technology on lunar regolith simulant. So hopefully by the end of this, there we go. Hopefully by the end of this talk, you'll have a little bit more idea about who Lucideon and the Amric Centre are, because we're fairly new in the space sector, especially the in-situ resource utilisation area. Then a little bit more of an understanding about what flash sintering is and how we're applying it to regolith, and then what's next. So yeah, excited to show you the results. Essentially, though, Lucideon is a materials development and scale-up organisation, and we have an end-to-end pilot facility. We do technology development, such as flash sintering. We do materials development. We have CMC capabilities. We work a lot in defence, aerospace, hypersonics, and other areas. And we also do a lot of contract R&D, analysis, characterisation, complex testing, things like that. The Amric Centre is all the kit. It's a lot of toys in a nice building, essentially, for end-to-end advanced ceramic processing, so powder manipulation, granulation. We work a lot in 3D printing of ceramics as well, which is a topic I'm hearing coming up. So a lot of exciting work done for many different sectors that I think is very applicable in this area too. So yeah, but on to what flash sintering is itself. So one of these key technology areas that I've been working in and the technical team that performed this project, it is the application of an electric field to a ceramic during its sintering process. So we're heating the ceramic, the furnace up to, let's say for the example that we're using here where we started, of yttria stabilized zirconia, a commonly used monolithic ceramic. We're heating up to 1050 degrees Celsius, and on the bottom right you'll see a video in real time. Sandwiched between two electrodes, we'll apply a electric field, and we see this rapid densification, this rapid sintering process occurring. So the interesting thing here is not only in terms of its ability to sinter ceramics at far lower furnace temperatures, but also the speed in which it does so. And then also the ability to control the microstructure. So along the bottom here, we're seeing different microstructures for the same density versus a conventionally sintered wire said sample where we see the grain size. So flash sintering in some of the academic papers is always headlined as, you know, sintered in under 5 seconds. We don't really care about that in sense of that headline. It can be minutes, it can be hours if we want to. Depends what we're trying to get out and how we want to manipulate that material. The way in which we do that is we've tried to make it a very scalable technology through enhanced thermal control, and that uses a proprietary software that we've written. It's a non-linear real-time control software. It's not as simple as just current voltage and time. There's over 20 sort of field parameters that we can manipulate, so ramp rates, pulses, hold times, things like that, and that's fed through to the system. So onwards then to how all this is applied to our regular simulant. So this project itself, and thanks to ESA for the funding for this work, because we aimed to show a feasibility study of flash sintering as a low energy technique for sintering simulant, and we used EAC 1A in this particular study. And of course that was the low energy part with the intention of reducing payload and efficient sintering and rapid heating processes. Pelleting first, though, it's an important part of it, and looking at the homogeneity and the pressing of your regular simulant. Looking around some of the posters and things, and we've got similar results in an independent study, which is fantastic. So we were pressing to 275 megapascals, and that gave quite a nice pellet. All the work you see is on 20 mil pellets, about 5 mil thick. And there's a little cross-section of the green body there that we formed. Okay, so first things we do in any kind of flash sintering project is apply some impedance spectroscopy to look at the electrical behavior of the material over a range of temperatures and try and get an idea. So regolith, in this particular simulant, it starts off very resistive, and then as we apply these fields, we can start to ignite conductive pathways, and indeed, what you're going to see here is that occurring. So if we play this video, we start to apply the electric field, we're getting some nice, and then all of a sudden we get the fireworks, which is... So what we're seeing here is we've ignited a melt and a localization point, and there's some thermal runaway there. So we're overcooking the middle and we're not touching the sides, essentially. And that's quite common, but it does show that the material's very receptive to electric fields under these conditions. So this was at 850 degrees thermal temperature, furnace temperature, sorry. We also tested some sieved powder to see if this reduced the tendency to localize, but had no significant effect, which is interesting. So we've skipped forward quite a number of weeks and months worth of work here as we optimize the field parameters for this. Okay, and the solution we came to, I'll play the video here, is essentially it's a pulse train where we are getting a high current pulse into the sample which thermally homogenizes as we go. So if we pulse these samples in an electric field for 5 minutes at a furnace temperature of 850 degrees, we can achieve the same as conventional sintering at 1080 for 1 hour. So we're really quite pleased with that, and we get a nice homogeneous sample throughout. And it's the way that in which we overcame the local thermal runaways and managed to get some homogeneity. Benchmarking against conventional sintered samples, of course, very important. So conventionally sintered in the same furnace, but with no electric field applied to varying different temperatures. And then we would measure the porosity and density, to which then we would measure the flash sintered samples as well for the comparisons. So that's how we reached those conclusions. And then, of course, there was some microstructural analysis too. So you remember the fireworks video before on the top there? That's the melting of the middle and not touching the outsides, as is evident by the SEM images there. But then we have our simulant materials, both conventionally 1 hour dwell at 1080 versus the pulse train method. And as I say, the densities were the same that were measured, but we do see a slight difference in the microstructures, and we'll discuss that in a minute. Okay, so before we go on to the microstructural and the sort of kinetics discussion there, the headlines being really that flash sintering has been demonstrated on 20 mil samples to homogeneously sinter in 5 minutes at 850 degrees, which we were really pleased with. We did some scale-up calculations as well, in the sense of we work on scale-up concepts, so one of the key applications for flash sintering is in the nuclear sector that we're a bit further down the line on. But we applied some same sort of scale-up concepts to this, and we're calculating a 50% energy saving and 35 to 40% faster versus conventional sintering, and that's cold to cold, so to speak. But the inhomogeneity of any regolith material makes sintering challenging, whether that using whatever technique. We didn't manage to have time to investigate any sieved material and improving the homogeneity of the pressed material in the first place. That's something we could look at. But then looking at the different microstructures, the handleability and the density were the same, but we did see more particle joining under SEM observation only, so we could zoom in a bit further in the next stages, but there was more particle joining for conventional sintering. So we're proposing that potentially the flash sintering mechanisms may change that. So this could be an athermal mechanism, i.e. liquid phase sintering. We're kind of igniting that kind of glass phase and gluing everything together, in which case adding more glass phase, as a previous talker was saying, could be quite beneficial. Potentially, though, that during the pulse, the heat is disproportionately deposited at particle surfaces, or maybe the pulse leads to a peak bulk sample temperature, which is significantly higher than the time average temperature that we're seeing that you would measure. So, some proposals here, something to think about, and something to investigate next time. But what would be next? Right, so we're really keen to get going and start making bigger samples, and of course getting into vacuum or a controlled atmosphere. This we feel would be potentially quite beneficial to the flash sintering process. It would allow less fireworks or less ability for those localized melt systems, because the breakdown strength in a vacuum would be far greater. So we could potentially have larger samples and a quicker process with a further reduced temperature. I see I'm over time, so I'll wrap up quite quickly. But also that would allow us to increase the scale and geometry if we can get more power into the pulse of the sample. And as I mentioned before, a little bit more of an investigation into the microstructure to show how the particle is bonding to give us those high density samples with flash sintering and confirming the new sintering mechanisms. I'll be around after for any more detailed chats on any of the subjects. But yeah, thank you very much for listening.
Thank you, David. Thank you very much. Oh, Jerry has a question?
Yeah.
So I may have missed it, but your flash pulse, is that an electric field? Is it a current through the regolith?
Yeah, it's an electric field. So yeah, we're passing the current directly through the sample.
Okay.
Correct. Yeah.
And what was the sample size?
20 mil diameter pellets and about 5 millimeter thick, I believe.
Okay.
Yeah, I think it said the exact thickness on the slides, but yeah.
June?
Well, I have a question regarding pelleting.
Yeah.
Based on your study, what is the optimized pressure of the when making pellet?
Yeah, I don't know the exact one because this wasn't a pelleting study. I don't know how long exactly they found. We did do the literature repeats of that we found some investigations that showed 30 megapascals, and that just was not sufficient. I've seen that some of the guys from Esric have also done some pelleting trials on a different simulant, and both are coming out that we're pressing at around 250, 275 megapascals, and they're very handleable and quite useful at that level of pressure. I can easily ask the technical team that did that work. If you want a bit more in depth, I can give you my email and we can find out.
So basically, in order to reduce the heating time, the more pressed, the better, basically?
Well, in this case, all the conventional sintering and flash sintering trials were undertaken on the same pressing parameters. Oh, okay. So the comparison should be irrespective of the pressing or the pre-processing. It was as received material pressed and then flashed or conventionally sintered. Yeah, but you are correct. The level at which you press it would affect the sintering mechanisms for flash or conventional. Yeah.
Okay, I see. Thank you.
Yeah.
Any further questions? Front row. We need the microphone for those online.
Do you see anisotropic effects applying the electric field, or do you change the direction?
All of this is using AC. I'd have to go back and talk to the technical team to look at that. It is all AC. We do see different. I didn't have time to mention it here, but we increased the frequency, and that improved the density slightly as well, and that will have a greater effect on larger samples and the depth of penetration, I would expect. Yeah.
Any further questions? No, thank you very much, David.
Thank you.
Thank you so much. And so the last talk, before we have a couple of other conversations, the last talk of Space Resources Week, it is you, no pressure, Xavier Walls from Carleton University, and you're going to talk about from regolith to aluminium additive manufacturing on the moon, a bench scale pathway. Xavier.
Hi, good afternoon. I think most of us are here trying to answer this question. We want to know, is it even possible to establish a sustained human presence on the moon and beyond? And in order to do that, that's why we're trying to work on space resources. And we're going to need them in order to build, for example, a lunar base or something similar. But in order to do that, we're going to need ISRU. We're going to need that because if we want to sustain operations on the moon, we would prefer not to depend on Earth-based supply lines. So basically, the resource that we're targeting in this project is lunar regolith. In particular, we know that lunar regolith is probably the best resource that we have right now because we still need to do some prospecting to detect specific ores on the moon. So currently we have regolith, we know its composition, and we know that one of its main component minerals is anorthite. And as you can see from the chemical formula, it has calcium, it has aluminum, it has silicon and oxygen. So most of those elements could be useful. And in this case, we're mostly working on aluminum because that could be used for construction, to build tools, and things like that. So the main idea of this project is to go through all of the critical steps for aluminum production on the moon, going from the chemical aspect and then going through the manufacturing. So in this case, we wanted to start with regolith, a lunar regolith simulant as our feedstock, and then explore all of the different processes to extract aluminum and manufacturing. So as you can see, we start with regolith, then we process it. We do some kind of pre-processing in order to obtain aluminum oxides or alumina. And once that we get that alumina, we electrolyze it to produce metallic aluminum. And then we go through manufacturing. So in this case, it's if you have a piece of aluminum, you can make a wire feedstock that could be used for additive manufacturing. So we started with this as our first step, so a very basic beneficiation. Our target was aluminum. So we use a very crude magnetic separation. So as you can see, it's just a magnet with the lunar simulant. So we put the magnet in contact with the simulant, and we try to extract as most of the iron particles that we could. And you can see a comparison there. So on the left side, there's an unbeneficiated material. And then on the right side, you can see beneficiated material. That's, of course, after leaching. So you can see that there's an actual difference there. Iron in general produces reddish colors. So there was a considerable difference between them. So after beneficiating the regolith, what we did was to do the leaching step. So that's the chemical reaction. But mostly we have our anorthite. We're using hydrochloric acid. And then we produce aluminum chloride extrahydrate, silica, and calcium chloride. So all of those elements could be useful. So you can see on the first picture, we have our regolith in contact with the HCl solution. And then you can see the products after the leaching. So on the bottom, or the precipitate, we got silica, mostly precipitated. And then the supernatant, that's mostly aluminum chloride hexahydrate with a mixture of calcium chloride. Then we separated both phases. So we separated the liquid from the solid phase, and then we did a calcination step in order to purify our components, remove any liquids. And as you can see, we were able to produce silica, that's on the left side. And then aluminum chloride hexahydrate, it's a bit of a different process. You can see that there's a reaction at the bottom. That's because aluminum chloride hexahydrate dissociates at high temperatures. So if you have aluminum chloride hexahydrate and you dissociate it, you're going to produce aluminum oxides. And then you're going to get HCl and water as byproducts. So the main idea of this part of the process is that we can recycle the HCl. First, we use it as the leaching agent. And then after going throughout the whole process, we can get it as a byproduct and we can reuse it. Then, well, at this point, we have aluminum oxides. So then the idea is to do electrolysis on the aluminum oxides in order to try to extract aluminum. So we worked on building an electrochemical reactor that could do that. So we have two images. So on the left side, you can see the external view of our reactor. So on the bottom, we have our furnace. Then we have the reactor itself, or the container. Then we have a cooling system on the lid. And then we have the electrodes and the inlets for gases and the electrical connections. And then on the picture on the right, you can see an inside view of the reactor. So in this case, our approach is based on the FFC process. So as you can see, inside the reactor, we have calcium chloride here. So this would be our electrolyte. Then we have our different electrodes. So in this case, as a first demonstration, we were using a graphite anode. But as it has been discussed, if we were to use an inert electrode instead of graphite, we could extract oxygen. And the cathode was made of molybdenum. We had a thermocouple to measure the temperatures inside of the reactor. And then everything was contained in a stainless steel crucible. And you can see the gas inlets, outlets, and the copper coil cooling system on the top. So these are some of our results from electrolysis. So the first image shows our first promising results. So basically, we have a comparison of one of the pellets that we were using on the left side. So you can see that it's very white. And on the right side, you can see one of our electrodes with the pellets. And you can see that there's a metallic surface or a metallic coating. So we did the chemical analysis, and we found that we had produced around 10% aluminum. But we weren't able to produce actual metal by itself. So then we kept improving our process, kept improving the electrolytes, the electrodes, the different variables in the electrolysis. And the second picture shows the first actual aluminum particles that were detached from the pellet. So you can see that there's a finger over there. So just as a comparison, it shows that the spherules were very, very small. And then the last picture shows successful aluminum production. So that's after standardizing the process, we were able to actually produce better spherules. Once that we got aluminum, we worked on the manufacturing part. So what we had to do was to remelt that aluminum and then try to produce something useful with that aluminum. So in this case, first we remelted the aluminum, and then we fluxed it to remove some impurities. And then we went through the casting process. So we poured that into a mold, and we made a cylinder. We removed any excess material. And after that, we worked on forging it. So basically, we have our cylinder, and then this has a squared cross-section because it's easier for it to go through rolling. So then we did the rolling part. That's mainly to make it longer, reduce the size of the cross-section, so that we could do wire drawing afterwards, because it requires a very small cross-section. And the last part was to do wire drawing with the aluminum. And as you can see, the last picture, that's a spool with the aluminum in the spool. And then the last part is electron beam additive manufacturing. We're using electron beam additive manufacturing to produce something with that wire. So basically, we worked on standardizing our process parameters. Electron beam, you have an electron beam. It acts directly into the aluminum. It melts it, and then you can deposit it into a build plate. So basically, some of the variables that we have to control were the voltage, the current, the beam diameter, the scanning speed, and the wire feed rate. Once that had been standardized for some aluminum alloys that we were testing, we used our wire, the one that we had made in the lab. So we had to test it because it goes through a rolling, the feeding system, it uses rollers. So rollers kind of press and pull the wire at the same time. So if the material is brittle or it has imperfections, it might not go through. So we tested that, it went through. And after that, we did some deposition testings to see if that's something that would work. So there's a video over there. So what you're seeing right now, it's just the electron beam acting directly into the build plate. So just to see if it was working. And then what we are going to do next is to start feeding the wire. And as you can see, we're depositing the aluminum on the build plate. And that's a picture of the actual deposition of the aluminum. And right now we're working on all of the necessary steps. So that's mostly analyzing the microstructure, the physical properties of the deposited aluminum. We're trying to 3D print some demonstrators. So basically, you can see that we're trying to make some cylindrical structures or some domes like the one on the bottom. Maybe trying to demonstrate that it's possible to print some type of gas tankage on the moon or something like that, but we were trying to print something that could demonstrate its use on the moon. And thanks for your attention. That's all. Thank you.
Thank you, Xavier. Any questions? Any questions for Xavier? No, no questions. Wonderful presentation and no questions. I think people are revving up for a swift exit. Thank you very, very much indeed. Thank you.